Yeah. Okay. So yeah, just I have to arrange somehow the the Zoom image, but okay. Yeah. So thanks a lot for inviting me to this seminar, which has a very interesting title, which really rings a bell in me, because I think this coherence, and especially cognitive coherence, is somehow a concept that is very important in opinion dynamics, and still not completely explored, I think. And in fact, some of the things that I will present are directly related to this notion of cognitive coherence. And I think also from a physical perspective, the concept is interesting because it gives rise to the possibility of specifying some kind of energy on opinions. So that you say, okay, cognitive configurations are somehow have less tension, so to say, and cognitive incongruence gives rise to opinion change. So I will talk about work that was done with Haval Shamon at the Forschungszentrum Jülich, which is a center that is a lot of involved in energy technology development. And he was doing there an experiment on attitudes towards different energy generating technologies, and the data is based basically on this work. So for this talk, I decided because also Katarzyna, how is your name spelled, by the way, or how?
Katarzyna, but in short, Kasia. Maybe.
Kasia. May I use Kasia? Okay.
Kasia is much better. Yeah.
Because Kasia asked me to give also a little introduction to the field of opinion dynamics, so I will do that. Then I will discuss a little bit more detail the basic setting of argument-based opinion dynamics, and introduce two extensions to these basic models that are also the topic of the validation later on. But before I come to the validation, so this will be at the very end, I will discuss the collective dynamics of these models. Is it right that I have about 40 minutes? Yeah. So I think this will be okay, but please indicate if I'm taking too long, because I don't know how much material actually has been gathered in this last 2 days. So opinion dynamics is a field that develops theoretical models of collective opinion processes to understand mechanisms behind emergence of consensus, polarization, and conflict. And the basic idea is that you develop computational models for the evolution of opinions in a virtual population, an artificial population of agents. And typically, so it's a multi-particle system, if you want. And typically a number of agents is placed in some kind of environment, which may be spatial, which may be governed by a social network, which may also be governed by some other forms of information. So, in this environment, agents exchange opinions in interaction. And so opinion dynamics is, I would say, is the field that studies the properties of these complex dynamical systems, mostly by computational analysis, but also sometimes, if possible, by analytical tools. And so the main idea is to understand the basic mechanisms of, let's say, qualitatively characteristic opinion developments, I would say, such as consensus, polarization, plurality, and also the influence of leadership, media actors, and so on. So typically we have a population, and typically we specify in the beginning, we specify just random opinions in this population, and then we employ repeatedly these interaction mechanisms and study the temporal evolution of this population. A lot of, let's say, at least for work in the last, I would say, 20 years, the most motivating aspect in opinion dynamics was what I call here the puzzle of polarization. So there were early works by Appelson and other people from mathematical psychology, in fact, that studied consensus processes and basically specifying a linear system and having like assimilation dynamics on the system. And there in such a system, you can only observe consensus in connected networks. So this is one of the key results also from Markov chain theory. So if you have a network where's a path from all agents to all others, then when you have an averaging procedure, you will go to one single stationary distribution. So these two statements that I mentioned here, one from Abelson and the other one from Axelrod, are really, really often cited in the literature. And I just read the Axelrod statement. If people tend to become aligned, tend to become closer in their beliefs, attitudes, and behaviors when they interact, why do not all such differences disappear? So, as I said, this is somehow the motivating questions behind a lot of modeling work. And it's also remarkable that just 20 years ago, there appeared two very prominent contributions in JAS, the Journal of Artificial Societies and Social Simulation, which introduced somehow bounded confidence as a concept to have stable plurality of opinions. So maybe some of you know this work. I will just explain it in 2 slides, I think, a little bit. So the motivating question is, how does a population with moderate initial opinions diverge into groups of agents that strongly support opposing views? Now, and when we talk about polarization, just to mention this, it's very typical to say an opinion is a single valued item, and we speak of polarization in terms of having a bimodal distribution of opinions, typically gathered at the extremes of the opinion scale. So this is the question, and I just briefly want to illustrate two basic, let's say, model classes. The first one I think is known very well to Kasia and the group, which is binary opinion dynamics, such as the voter model, your models, and also Serge Galam models, which is directly related to a physics analogy of Ising spins. I think you coined the term of spintons. Is it correct? Right?
Is it yeah, it is correct, but I mean, it's not really popular. So, but yeah.
Yeah. So we have basically a binary decision per agent, and I just usually we have opinion change in interaction, such that just there's an imitation, a copying mechanism, or we may have we may look at the neighborhood of an agent and adopt the majority opinion. One can also go a little bit further and analyze best response dynamics, which is related to majority opinions. And in this context, many theoretical results are actually available. And I would say that, so for instance, physicists, and you know much more about this than I know, you typically study order-disorder transitions in these systems. One possible focus is on convergence times, etc. And so the social network plays a crucial role for applied analysis, let's say. And what one typically may observe in this is the example of majority rule or best response dynamics, where you have this spatial clustering of opinions into red and blue clusters. So if you have any questions in between, don't hesitate to ask. the other class of models that I just want to briefly illustrate here is based on a continuous representation of opinions. So opinions are typically on a scale from -1 to 1 or from 0 to 1. This somehow let's say, the history of these models comes from this psychological work on group dynamics that I mentioned earlier, where you basically have, let's say, you have a population of individuals and they may be connected via a network, and then you have an averaging dynamics so that they become a little bit closer in interaction. And I think one of the first of these models is by French in 56. And there's a whole theory developing out of this due to Friedkin and Johnson, which is called social influence network theory. And they also did some very interesting empirical work, but focusing on small groups, basically. So opinions are just points on a continuous scale, and opinion change is typically a weighted averaging procedure of the agent's opinion with opinions in the neighborhood. And one of these, the core innovations, let's say, like 20 years ago, was to introduce bounded confidence as a simple form of opinion homophily. So homophily is a very important concept in sociology, which relates to the tendency of interaction of similar agents. So we tend to have more interaction with others that are similar to us. And this is a very robust finding in sociology. And one can put many of these models into a conceptual scheme that is as follows: similarity leads to interaction, and interaction leads to still more similarity. And some of the things that have been studied in this context are the influence of extreme or stubborn agents and social bots and etc. Basically, just to mention this on the right-hand side here, what we see is basically the evolution of this kind of model with different values of bounded confidence. So the lower one is a model where you have, let's say, high confidence in others. So you just take into account all opinions independent of the opinion of the other. And then when you slowly, let's say, decrease this confidence, so you say, okay, I am at opinion minus 0.5, and the other one is at plus 0.5. I don't care about what he's saying. I don't adapt. Then you start to observe plurality. So you have a local averaging, but it's no longer a global averaging. So you have to stable.
So Sven, maybe
yeah.
I will only add that you have the time, because I don't know if everybody knows that you have time on horizontal axis, and each line corresponds to opinion of a single agent. Yes. So like.
Yes. Yeah. Yeah. That's good. So that's a very good remark. So typically in these models, you start with a uniform distribution here from 0 to 1. And then you have this averaging procedure, and what we see here indeed is the trajectory of single agents that coalesce or just fall onto each other.
I have a question, because you represent these agents on a line, but there is some kind of topology of this network behind it, right?
In these models, typically not.
So everyone interacts with everyone?
At least in the let's say foundational models here, it's everyone to everyone, and in tendency in this class of models, the network doesn't play such a crucial role. So it's more about maybe looking at let's say influence weights. So you may say there is a single agent that somehow has the power to influence others more than he is influenced. So these topological variations are studied, but I would say in the network doesn't play such a crucial role as it plays in binary opinion dynamics. But I think it's a very interesting point, because it points to somehow a combination that is not yet fully explored, I think. Now, to argument based models, here let's say the motivation behind developing argument-based opinion dynamics is to gain more complex and arguably more realistic representations of opinions. And I just want to mention the core assumptions here, which basically one can say that argument models model collective deliberation processes, and they model this by a social exchange of pro and contra arguments. Here the focal object, or what is called in psychology the attitude object, is a certain issue, and you say, okay, you have information that speaks in favor of a positive stance towards this issue, or against it, so disfavoring it. And this is somehow really closely related to a structural series of attitudes in psychology, such as the AB scales from Fishbein, actually developed as a measurement tool. So where you say you have a certain object, let's say a car, and you have certain attributes, color, velocity, and so on, and you have an evaluation of these attributes. And so if you want to measure an opinion towards a car, you typically ask a survey battery addressing these attributes. Or at least this is one way, which is mostly related to structural attitude theory. So what in relation to this previous two model classes, what we can say here is that we have a representation of opinions that is multidimensional and multi-layered. And the actual exchange mechanism takes place on the lower level of arguments. So agents exchange arguments, and the attitude is actually, if you want, an epiphenomena of this underlying argument distribution. So in the simplest case, you would just count the number of pro arguments, which is indicated here by the plus, and versus the number of contra arguments, which is indicated here as the minus. So in this case, you have two pro arguments and one contra argument, giving an attitude of plus one. So I have some other examples here, and this is precisely also the representation that I use in all what follows. So I will use the setting that we have 4 pro arguments and 4 contra arguments. And this means that we have an attitude scale of -4 to +4. So it's a 9-point attitude scale. And this is important when linking to data, because there typically you have a specific scale. Often it's 7 or 9 point, maybe more, maybe less. But this is important to just have a conceptual matching between the empirical assessments and the models. So I hope this is clear. And now the general update process in argument exchange models is that you have a social interaction part, and you have like an opinion adaptation part. I would call it here cognitive processing, because this will come just in a bit. Notice again that most models in this paradigm do not intensely play with the interaction network. And also all what I show here is based on a single network, on a complete graph, if you want. So so the process of these models goes as follows. You have a number of n agents, and I pair them at random. And then I have the first one is chosen as a sender, the second one as a receiver, and the sender articulates a randomly chosen argument and to the receiver, and the receiver adopts this argument in the simplest case with a probability of 1/2. So just a random adoption. So this was how they were introduced, I think this is the paper. There are actually 2 from 2013 by these authors that introduced this model in a slightly different form, but the behavior is very similar. And addressing the puzzle of polarization, showing that there is a transition from consensual dynamics to bipolarization when you increase from weak to strong homophily. So,
could you Sven, repeat how this homophily enters this model? Because like you choose a pair randomly, and then you choose one of those arguments, and then you copy this argument with some probability. So where is the homophily?
The homophily, this is a good point. I forgot to make this clear, because this is, I think, from the mathematical point, the crucial aspect. We have the attitude, the homophily mechanism acts at the attitude layer. So not at the argument layer, but at the attitude layer. And so if you say you have an homophily or a confidence value of 2, in this case, then these both would just not interact. Well, in this case, they are relatively similar, but let's imagine you have here a plus and here a +4 and here a -1, then with reasonable assumptions about homophily, they would not interact. And so just to maybe illustrate what happens to create this bipolarization, there is a finite population effect, because as you run this process, the homophily generates let's separated argument pools, so that the groups that approach this 2 different extremes here and here, they just rely on distinct sets of arguments, and so this is basically the mechanism that leads to polarization in these models. And I think they're studying the transition from finite systems to infinite systems is a very interesting problem. But I want to I will come to this a little bit later. I will, let's say, propose 2 extensions to these models, which I think are reasonable. The first one from a psychological perspective, and the second one from an applied perspective in terms of media effects on these systems. So the first extension is bias processing, and so a favoring of certain arguments that support the current opinion. This is also called attitude congruence bias or attitude defensive processing. So typically, humans process information in a biased way, such that attitude challenging arguments are downgraded and attitude supporting arguments are upgraded. And this is precisely what the experiment that I will talk a little bit later addressed and measured. So what we integrate this into the models by just saying that I just briefly go back to this one here. Yeah, here we have said that we have a random, just a random decision. Basically, we throw a dice if the argument is adopted or not. And this is the place where I plug in bias processing by saying, okay, we have no longer a probability of 1/2 to adopt or dismiss an argument, but we have a probability that depends on the current opinion. Is this clear, more or less? So in this case, I just show the probabilities for receiving a contra-argument. So an argument that speaks to a negative opinion. And here we say that if the agent already has a negative opinion and we have a strong processing bias, then he will have a probability of 1 or close to 1 to adopt this argument and strengthen his current opinion. And vice versa for the other. So just this parameterization of bias processing contains the previous neutral assumption. Namely, if I set beta to 0, so I have basically it's an inverse temperature term, if you want, in the physics terminology. So you go from a random choice to a choice that is more driven by current opinion. And so this is the first essential parameter, beta, which accounts for the strength of bias processing. The second extension that I want to introduce, and I use the parameter rho to exemplify it, is that I have an unbiased external signal that that may come into the process. So typically, if rho equals 0, then we just have the previous dynamics that we choose another agent and then send a receiver dynamics. And the argument is adopted with a certain probability. But now we say, okay, information may also come from an external source, and rho determines how frequent this happens. So this is basically the two extensions that that I want to study in the following.
And sorry, an external source of information is that you just it's constant, so it's like always in favor of something, or how it works?
The social information.
No, the source of external information.
So it's unbiased.
It's unbiased.
Yeah.
Okay.
But this is an interesting thing to play with, actually, because it would also be measurable to a certain extent. I think, but now for the moment, it's just you basically choose a receiver, then you have a probability of rho, which you say, okay, choose another agent and run the process, or choose or give just a random argument.
So it's like the noise.
It's like noise. It's just noise. Yeah. So what I want to discuss now is the collective dynamics which it gives rise to, and I would like to do this with rho equals 0, so without noise first. And this is also what the paper that I sent you before just studies this without noise. So a little bit on the phenomenology of things that may happen in the model, which I think is already quite rich. Here I have 4 trajectories where in all cases so time again is on the horizontal axis, and here the attitude from -4 to 4, which is initially a binomial distribution. So this comes by the fact that I assign random arguments to the agents, and this means that I have a binomial distribution on the attitude level. So we start from this random distribution, and from top to bottom, we increase the processing bias. And what we observe is that in the first case, so in the original model without bias processing, we have a very long, so it's extremely long trajectory, which leads to this consensual dynamics. So all agents coordinate in a certain on a certain opinion. When we introduce a little bit of bias, then this process is extremely accelerated, and we have this what I call choice shift, or one can also call it extreme consensus. So the whole population just goes to one or the other side. When we increase bias processing further, we observe that there is a metastable intermediate regime of bipolarization. So bias processing leads to this that opinions are reinforced, and they are reinforced for 2 groups independently in a sense. But this is metastable because due to finite populations again. So once you have these 2 groups emerging, then you have a different process of, let's say, competing groups, and slowly you have transmissions, and then by drift you go just to one side. But what is notable is that this metastable phase can get really long, can get really persistent if you increase the processing further. So again, here you see that now I have 20,000 steps here. Let's see, is it 20,000? Yeah, 20,000. I have 40,000 steps here, and in between you have a very quick process actually. And I think this is an interesting. This is from time perspective. This is very interesting, and want to, or I think even that this may somehow be contextualized in the context of evolutionary dynamics, in the sense that it shows that when you think of a group that has to take a decision, yeah, cohesively, then it's really favorable if the whole group goes to one side. And so a weak processing bias, a weak cognitive bias enables such a quick decision process. And so I think this is a very interesting observation in this models. So there's this transition when you introduce a weak bias, but there's also another transition that we have seen, that we have this metastable state of bipolarization if this bias becomes long. So then the group will enter into intra-group conflict. What I show here basically is when I vary through the strengths of bias processing better, I have the probability of entering such a bipolar regime in blue, and I have the time we remain in this regime on a logarithmic scale here. And what we see is that there's really an exponential growth of this convergence times, or of the persistence of this metastable bipolar regime. So addressing the puzzle of polarization, again, what this paper shows in this context, let's say, is that bias processing, if it is strong enough, is sufficient to generate persistent bipolarization. And this is basically the preprint that we have on this, and I hope that it will become published. So it's in second revision, but in sociology, it's very slow. Yeah. Okay, so now I want to briefly discuss the collective dynamics with noise. So having a rho larger than 0, so that we have this run. Basically, noise is the best term, actually, if we think about it. How am I with time?
Yeah, so because we started much later, so I think that you can talk for 10 minutes more, maybe. Okay.
Very good. So the dynamics with noise. So I just go to the level of observables already, without showing the trajectories, but still, I think the general, let's say, the behavior that is possible in the model can be characterized by two observables, which is basically the shift, so which here is the absolute value of the mean, and the diversity. So a high shift indicates that the population just goes to one side. Yeah. So if all agents are at +4, then I have a value of +4, and it's in this observable. Whereas bipolarization and also consensus, they would lead to a mean of 0. So this differentiates between these two, and in order to differentiate a bipolar configuration from a consensual configuration, we use the diversity. So basically the standard deviation. And what we see is, I think it's a very interesting phase picture. And I just want to mention already that I think from the physicist perspective, this transition is a very interesting object. So because it's really surprising, you have a very sharp transition from going from a distribution that is basically, let's say, a little bit broader than normal, to a distribution that is just concentrated at one side, and it's very quick. So what I did to classify basically the characteristics of this qualitative distributions that come out of the model is by comparing to some stylized opinion distributions. So we have this extreme consensus here, we have a neutral consensus, which doesn't play a role. We have a condensed distribution, a normal distribution, like the initial model conditions. a uniform distribution, and bipolarization. And what I do here is just to compute the Shannon divergence between these distributions and the model outcome distribution. So I run the model, basically, I look for the stationary distribution by looking at a certain final time period. And then I compare this, and what you see here is just let's say, the model outcome and the closest of these stylized distributions. And we have a very, I think it's quite informative about the different types of transitions that happen here. So if the noise is very strong, or basically one, then you go from just this normal initial distribution, and you get broader, and you go to the bipolar regime. If social influence is active, then we have in between, we have also this dynamics, but then we have this, and then we have this. So this is basically the transition structure of the model. And just to what I also look at, because it's typically at the transitions, you have a high variance in the results. And what I find, and what I find at least a little bit surprising, is that we don't have such a high variance here. So it's really a sharp transition. And so maybe this is a possibility for future discussion on this model. So now I have a little bit of time for addressing what actually was the title of the talk, and I hope it's not already too much for the heads after lunch. So let me briefly somehow introduce the idea of validating opinion dynamics models at the micro and the macro level with these survey experiments. So basically, a survey experiment is just a very simple experimental setting where you ask people about opinions on a certain issue or a set of issues, and then you have some kind of treatment. So, for instance, you give them arguments on the issues, and then you measure again the opinion. And what this yields is basically, from this first assessment of opinions, you have opinion distributions, macro scale, if you want. And from the second assessment, or the comparison from before, after, you have attitude change data. And these two types of data, one is for the macro validation and the other one for the micro validation. So I will this is my colleague, and I'm really happy that we meet on these topics. And actually, the experiment was run before we had the model. So, but it fitted so well that we just had a really good collaboration on that. And the idea of this argument, of this experiment, was that agents report their opinions on 6 different energy generating technologies. And then we have 6 groups of agents, and they receive 7 pro and 7 contra arguments for one technology. Then they rate the persuasiveness of, or the quality of these arguments, and then the attitude is measured again. So this is precisely this setting, and just here we have it again. And so this means that we have macroscopic data, if you want, from 1,078 subjects that reported opinions on 6 different issues. So coal, gas, wind, onshore, offshore, photovoltaics, and biomass. It's really a pity that nuclear power is not there. It's really a pity, I think. And attitude change data, we have this 1,000 people split into the different groups. So it's reasonable numbers. And for the micro level calibration or validation, we ask how well does the microscopic model of attitude change that we use with the bias processing procedure fit the experimental data. And what the main idea is having, let's say, a virtual agent model. We can not just use macroscopic simulations, but we can also simulate an experiment. And what we ask is, how would artificial agents react to the same experimental treatment? And I will not go into the very detail of this, but we can, in this argument model, we can analytically compute the expected attitude change when agents receive 4 pro and 4 contra arguments. And the basic idea is that we compute how many new arguments are adopted by using it's combinatorics, and what is the respective attitude change. And what we arrive at is a response function that we can match with the data. And the response function is basically parameterized by the strength of bias processing beta. And again, we see that when we have no processing bias, there is attitude moderation, which means when agents receive balanced information, yeah, it's pro and con, and they have a very negative opinion, they will just moderate. Yeah, they will go to plus, they will change +2. Whereas when we have a strong processing bias, and let's say an agent has a negative opinion of -2, then we will see that even if the information that he gets is balanced, he will go 1 step to the negative on average. So from the psychological perspective, this is very interesting, and we have some. One can make a simple bifurcation analysis to really have this transition from moderation to polarization. I will not show this here. I would like to just show the result for let's say the single technologies when we perform a least square error between the theoretical prediction and the data that we have. And what we see here is that on the all data, we have the best fit around 0.5. When we have beta 0, which is the assumption made in previous models, we have a very, it's worse. This is, I think, the main argument here. So the neutrality assumption is not valid. And we have interesting variations regarding gas and biomass here. And I think one explanation is that they are more recent in the debate. Yeah, so let's say the cognitive, the opinions, the arguments are not already settled. Whereas in all the discussions, solar, coal, and wind, we have a very strong or a stronger processing bias. So now the question at the macro level basically is, how well do model outcomes, so the opinion distributions that we observe, fit the surveyed opinion distributions? And here I just show the empirical target, so to say. When this is data of the 1078 subjects, and it's just the distribution of opinions on this 9-point attitude scale. And here we see that coal is more negatively cited, and the green technologies, let's say, are more positively cited. And gas is somehow a special case, which is it's broader than a normal distribution, but it's not already settled somewhere. And for comparing the model outcomes to this data, we take the same approach that I based on the Jensen-Shannon divergence, as I mentioned earlier. So we just look at the model outcomes in this parameter grid and look where is the best fit to the data. And what I show by the white dashed line is somehow the best fit of the micro calibration, just for a comparison. I'm not through with having a clear conclusion on that, but I think that it's at least remarkable that we have somehow a good micro and macro fit in a similar regime, let's say. But as I said, I have to think a little bit about what this actually means, and also what it means to have the micro and macro assessment on the same experiment and so on. So there are conceptual questions that are not completely true. Now, just to this is the finishing
Okay.
You wanted to indicate this, right?
Yeah.
But I want to show you just that you see how well the distributions are actually matched. So let me so this is a tool that I developed. It's already some years ago. Now where I just have in blue the model dynamics running. I just have a pause now, and in red I have the different empirical distributions. So here I have the situation for coal. If I go to gas, we have this, and if I go, let's say, to photovoltaic, we have these distributions. And now if I run the model, so let me check. I will just start with a let me go like this. So if we run the model here, we see that okay, the distribution of opinion evolves in time. I can make it a little bit quicker. Now we see, oh, okay, it's reversed because the model is symmetric, right? So my little trick always is to go to coal. No, but what I think is more maybe more interesting is now when we introduce new news or noise into this model, then we really have a stationary distribution that matches very closely to the data. So in this case, we are yeah, let's go. So this is basically the stationary distribution that we observe when we have these parameters here. And so if we let's say we increase this, then well, you see that in this parameter space you have certain parameters that fit very well to these distributions. And just let me restart and hope that it goes to this direction. So yeah, so here we see that there are really, let's say, there are parameters in this space which really remarkably closely match these empirical distributions. Okay, so I would like to thank you a lot for your attention, and maybe we have some points for discussion.
Yeah, thank you very much. Yeah, I have a question, but maybe before I ask, maybe some other people have also some questions. So yeah, now it's time for questions. So do you have any questions or comments maybe? Okay, maybe let me start. So my question is like, I have two, but the first one is related to this experiment. So how do you validate the social influence? Because what you are doing, you are showing people some arguments. So it's not like really like social influence in a sense that you don't control if indeed it's like pairwise interactions, that you have one guy and exchanging arguments with another. I'm asking because in our models, usually we assume that you need some group that influence you in order to convince you to change your mind. So how would you validate that one person is enough to convince you?
It's another question. It's a question that was not addressed, I would say, with the experiment, because the experiment was really focusing on having unbiased information, having neutral information signals, so to say. Is bias processing sufficient to lead to extreme opinions?
Yeah.
And the reason is that there is a whole, starting from the 70s, whole experimental programs that ask this question. Okay. About how we should do it in order to assess something like the real impact of social influence. Psychologists would study source effects, I think. So they would somehow say, okay, this information comes from that person or from this enterprise or so on. I haven't done any experiments where we have a real social mixing, and I think also so let's say the very nice thing of this experiment is that it's really clean.
Yeah, that's true. That's true. Otherwise,
if I go to having some kind of group discussion, it's really difficult to have such a control.
I also like this experiment. For sure, we will look to this, and also because we are right now working on multi-state models. So still discrete models, but multi-state models. So for this this experiment is also very nice. And another question is related to this sharp transition. So like now I'm asking as a physicist. So indeed you had small deviations and very sharp transitions. So it seems like you would have like this continuous phase transition on this border. That in our nomenclature, we divide all transitions to continuous and discontinuous. And if you have discontinuous, it's usually very sharp. And also you don't have this huge fluctuations. That's why I'm saying, but to really check if it is discontinuous, usually you see also something which is called social hysteresis. So then you would need to check another initial condition and check if the transition will be at the same place.
Okay, so it's not a backward.
You can go backward, but it's not like, usually they draw it like this, that you go from this direction and this, but it's not that important. The important thing is that your results depends on the initial condition. So if you start from any other initial condition and your stationary distribution will be different for these values of parameters, then you know that you have this continuous phase transition.
It will not be different.
It cannot be different?
I mean, from the tool that I showed in the last, just at the end, my experience is that it will not be different.
Okay.
So, but just having this tool, I haven't checked carefully, but I just see that it really follows the.
Okay. It's not the proof, of course, because sometimes you don't have hysteresis and still this continuous phase transition, but but this is something we can look at.
I would be very happy to have. So I know a little bit about this, the phase transition literature, but of course not enough to really be sure when speaking about it. So
And another point, sorry, maybe some other questions, because then I will ask Arek, you would like to ask something?
Yes, I'm just wondering, because in your model, each agent interacts with everybody else, yes?
Yes.
With this bounded confidence, let's say, effect, yes?
No, I thought the bounded confidence is not there.
Okay, so have you tried to use some kind of Millfield theory to predict the behavior analytically? Because if we have this interactions to everyone in the system, this could probably work.
Yeah, we have done it for a very simple, for a very small model. So having just I think just one pro and one contra, or two. I'm not sure in the moment. I think. But
you use this Markov chain approach, yes, to do this, or not?
No, this was really a mean field-like approach, where we, I mean, what we do is basically to specify the master equations, and then we try to reduce the system so that we can have a dynamical system description which can be solved. And it was just the setting. Okay, you have one attitude and you have one pro and one contra argument. And there we could do something, but what, in order to relate it to the simulations, what I didn't really disentangle at the moment was this transition from finite to infinite populations. Because what you see in the mean field is that you go to a certain manifold, but then you have this drift and then basically you drift on this manifold to have convergence in the finite system. And so when we looked at the let's say, well, our approach was really dynamical systems theory. So we had reduced differential equations and could compute, for instance, the fixed points. But these fixed points, they were just they were not corresponding to what you see in the simulations due to this finite size drifting dynamics. And somehow we didn't follow this this further. Actually, we have a paper that is now in silence since 3 years. It's not a paper; it's just a draft of things. So I would be very interested to somehow have new ideas and continue this line of thought.
Okay, maybe I will stop recording because maybe